Welcome to the course on two-dimensional signal processing principles and practices. We are doing the 2D FIR filter design. Window method we have done, and the frequency sampling method we have done, and frequency transformation also. The one design procedure we had seen, the other design procedure of the frequency transformation method, which is linked with the first method, can be devised as follows. That first one, the method which we had known the specification and then of a 2D filter, and then we passed on to the 1D filter and designed that 1D filter, and then corresponding T of n1 comma n2, that is a transformation function corresponding time domain or the space domain samples they have been found from h of n, the known 1D designed coefficients, and then the T of n1 comma n2 that is obtained from transformation method. The samples we can obtain the coefficients of the 2D FIR filter. That's what the first method is. In the second method, we can see the same procedure in which the transformation function which we had taken as known in the first design procedure, assuming that it is not known or closely known procedures or the used in practices can be done, and so that this method assumes that first step as a design of T of n1 comma n2. So from the transformation function, frequency transformation function T of omega 1 comma omega 2, you have to obtain this through the inverse transform. That's what we say. So now first step is to design this and then translate the given specification. So in 2D, h of omega 1 omega 2 to h of omega 1D, and using this h of omega we design h of n, that is using the window method or Park-Maxillin method. So any of the procedure can be used to design this 1D, and knowing this h of n and T of n1 comma n2 as we did in the design method 1, so we can obtain the filter coefficients here h of n1 comma n2 2D 1. So the first step is to obtain this. So is there any transformation function will work, or what is the transformation function which can be used for the given specification? So that's what the one specification we had, Park-Maxillin transformation itself we had seen in the first example of the design method 1. So now coming to the design method 2 of this filter specification is given as supposing the elliptical contour. Like the passband contour is something Cp which is having omega 1 square 0.5 pi and 0.5 pi square plus omega 2 square by 0.6 pi square equal to 1. So if we have the contour in this fashion, which is varying with respect to omega 1 and omega 2 as an elliptical one, similarly the contour for the stop band contour also, instead of having the circle which we had taken in the previous case, so then this omega s equal to omega n square by 0.6 pi the whole square plus omega 2 square by 0.7 pi the whole square equal to 1. So these are the specifications we can say that it is given for the, so 0.5 and 0.6 can be considered for the passband frequency and stop band frequency, and the ripples allowed in the passband is 0.08 and the ripples allowed in the stop band is also 0.08. We have very minimal ripple or the tolerance in the passband, and the stop band we can see. So if these are the specifications, then considering these specifications we can in 1D, so we can use this is given in the 2D, and what is the specification in 1D, and we consider the same thing in the 1D also and proceed with the design. So to visualize this specifications, the omega 1 and omega 2 in 2D, minus pi 2 plus pi and minus pi 2 plus pi, this contour of passband and stop band are given as elliptical one. So you can see that in circularly symmetric we had looked at this as a circular one, and in the separable performance or the separable frequency response, in which that we had taken this as a square using the rectangular function. So given this contours of passband and stop band, and the in between band is this transition band, in which we can say, we can also check this in the low pass filter characteristics, where omega p is this and omega s is this. So the transition band is between them, and omega p is here is 0.5 and then 0.6 have been given, and then this transition band which is given here. So here is the ripple which is specified 0.08. You can say 1 plus delta p by 1 minus delta p, and this is what the delta s also having 0.08. So this is 1D low pass filter specification, in which now having this low pass filter and the stop band and the pass band case, we'll use that in the design. So for that, first step is here in this designing the T of n1 comma n2. So for designing that, what is that to be taken here is the transformation function which we have considered T of omega 1 omega 2 are the one. Now we are going to find this T of omega 1 and omega 2 in this method. So considering cos omega or cos omega p and cos omega s, pass band and stop band frequencies, then equal to T of omega 1 omega 2 in the respective contours belonging to omega 1 and omega 2. So if this is the assumption we had taken in the previous example also, and we have considered this is known in the previous design method. So now the thing is cos omega, which is for the omega p region, that's a pass band, which is T of omega 1 omega 2, also having the omega 1 omega 2 in the region of support is pass band, and which includes the RP, that is pass band region. And in the stop band omega s to pi, where omega is between this, when cos omega varies from this to this, T omega 1 omega 2 also having the region of support RS, omega 1 omega 2 is belonging to RS. So RS includes the here this band, which is the stop band actually. And then we can have the steps for step 1 itself, or in the step 2 we will proceed with the specification and then the 1D filter design, and then getting this T of n1 comma n2 and then h of n, and then getting the h of n1 comma n2. So here we have this first assumption, the shape and size of the region of support of T of n1 comma n2, because this needs to be found until we know the samples obtained from the frequency transformation function, will not be able to get the coefficients h of n1 comma n2. So T of n1 comma n2 to find it, or we will find the shape or the region of support for it. It is a first quadrant support, or it is a second quadrant support, or it contains all the region of support by 3 by 3 which we had considered in the previous example, and so on. So the case of this one is becoming very simple if we have the FIR filter coefficients or the zero h of n equal to h of minus n, or we can have the zero phase or the linear phase structure. So impose a structure on T of n1 comma n2. That is the first step in getting this T of n1 comma n2. Assume that these are the coefficients required of T of n1 comma n2, and then you use assuming omega p and omega s, and then design this T of n1 comma n2. So that how do we design it? It's approximately equal to T of omega 1 omega 2, which is in the contour belonging to this, has the omega 1 and omega 2, and similarly omega s. So this one is becoming at least not equal to, now it has become approximately T of omega 1 comma omega 2. So the coefficients we have to consider assume this T of omega 1 omega 2 and to find this T of n1 comma n2 in this case. So and then using the case of this T of n1 comma n2, if it is okay, or the design T of n1 comma n2, what we got from that h of n1 comma n2 using h of n, and get the frequency response of the filter 2D FIR filter. If that is not proper, then we can get T dash. We can further refine this support what we obtained here in the first design. That means the iteration can be done to get the new T dash n of n1 comma n2. So this process to start with, so assume that n1 and n2 are between -1 and +1. So the T of n1 comma n2 equal to 0 for the supports outside this, we can say -1. So the outside this support, this would be 0. So it is available only -1 to +1. So here n1 and n2 we have, and this is -1, and here similarly 1 and -1. So this is available for these points only. So the rest of the points it is 0. So fixing some region of support, it can be 5 or it can be of more than that as well. But for practical cases, we can use this as 3 by 3 region of support, and the rest of them it is 0. So to finding the coefficient also would be easier. So and imposing the symmetry on this region of support, that can reduce the number of coefficients estimation, simpler or easy. So T of n1 comma n2 is taking T of minus n1 comma minus n2, that is 1 1 is equal to 1 1 minus 1, and so the twofold symmetry restricts the coefficients to be estimated. So this is twofold, and if you make it fourfold even, that minus n1 comma n2 is also equal to n1 comma n2, then it further reduces the number of coefficients to be estimated for this. So right now fixing this region of support as the first, because it is unknown, and then giving the twofold symmetry or the imposing the fourfold symmetry even, so to get the number of coefficients less. These two symmetries are imposed on the assumed T of n1 comma n2, and if we assume that T of omega 1 comma omega 2 is going to be a linear combination of cos, right. So this is the previous transformation function, Park-Maxellin one we have considered. So the same function we have taken, but these constants are made it as unknowns, a, b, c, d. So this coefficient should be approximately equal to cos omega p, and it's equal to cos omega s, and then we find this coefficient a, b, c, d. So that is the solution for the frequency transformation function. So these constants, how do we get these constants? So now the equation is this, the generalized equation, we can take it omega and omega 2 for this particular region of support, and then cos omega is making it equal to T of omega 1 omega 2, making this equal to cos omega, but omega equal to some condition needs to be imposed so that these constants can be found. So if you put omega equal to 0 in this case, this becomes 1. So the whole equation is equal to 1, and at the same time it will be in terms of omega 1 and omega 2. So to solve it, keeping omega 1 and omega 2 also equal to 0. So then it would be all this equation will be reduced to 1 equal to a plus b plus c plus d. So that's the equation we get. So we get one equation for a, b, c, d, and the other equation can be imposing these omega 1 and omega 2 equal to pi. So for this, some T of omega 1 omega 2 equal to pi for the same omega, so we can get the other equation as well. So you keep using these two equations, and there are 4 unknowns anyway. So we impose the condition of omega 1 and omega 2 for various omega, and we can solve this a, b, c, d like that. So the a, b, c, d can be solved, and for imposing one more case of omega p equal to this omega p equal to, instead of 0, we can have this omega p as 0.6 pi or 0.5 pi omega s. So then we can get the other constants as well. So we will have these 4 such things here, imposing that omega equal to 0 and omega p omega s equal to that values and omega equal to pi. So we will get 4 equations, and then we can get the transformation function solved. The constants can be obtained. So this error, so how do we get this or how do you make sure this one going to be the solution? Or we have to, there will be many solutions if we have this for the region of support to have this cos omega, the contour, and the T of omega 1 comma omega 2. So to restrict it, make the error equation in which cos omega p equal to T of omega 1 omega 2, and this error between this error square, integrate it, and the similarly for cos omega s, we get a contour, that error between these two square T omega 1 omega 2, integrate it and add them together. This is the error, common error, and this error is less, then we can consider that that solution, that what we get for T of omega 1 omega 2 is a transformation function. So this such function is done here. T of omega 1 omega 2 equal to, it's giving minus 0.47, 0.67 and 0.47, also 0.33. So ABCDs are obtained in that fashion for different cases of the equations what we got. So having this one, now once we have this T of omega 1 omega 2, take the inverse transform of it, and then we get T of n1 comma n2 from this. And the next step, as we did in the case of the first design procedure as well. So taking this h dash of x, which is h of omega, where h of omega we have to substitute as cos omega, and this equation is known. We have to find this h of n from using the 1D FIR filter design method. It can be of window method or the Park-Maxellin algorithm, any of this, and get this h of n. So this is how this is the same as the equation which we have used in the design method 1. So these equation, getting this h of n and then T of n1 comma n2, from this get the h of n1 comma n2, that is the process. So now if using that h of n1 comma n2, plot the frequency response of this h of n1 comma n2 and see that how the response would be. If further refinement of the response is required, so the contour response, if we are not able to get, or there is a process, the further refinement can be done for this even by changing the transformation function. So what we had got, the T of omega 1 omega 2 may not be exactly giving the response what we have aimed for, but the further refinement also possible with this T dash omega 1 comma omega 2, obtaining this transformation function better. So the case of what we had obtained, that coefficients will be further refined to have the better response. In that case, the iteration can be tried. So one such iteration can be T dash of omega 1 comma omega 2 equal to k1 T of omega 1 omega 2 plus k2. So the T is not simply taken, it is multiplied with some constant k1 and k2. So what is that k1 is practically used for, k1 and k2 values, that is going to be 2 by T max by T min, that is minus T max plus T min by T max minus T min. So these are the standard procedures which we can follow. The k1 as related to T max and T minimum. T max and T minimum are the maximum values of this T of omega 1 comma omega 2 and the minimum value of T of omega 1 comma omega 2. So with this we can get the case of T dash, also assuming between minus 1 to plus 1, in which all the values of omega and omega 2, in which this T dash is also should be assumed, putting one more constraint on it, T dash should be within minus 1 to plus 1 to simplify the estimation here, the coefficients of the T to get it, and we can get this T dash n1 comma n2, it's equal to k1 T of n1 comma n2 plus k2 del of n1 comma n2. So this is the inverse transform of T dash omega 1 comma omega 2, and its inverse transform is T dash n1 comma n2. So k1 k2 which we obtained from this can be substituted here. So with this equation, what is obtained for this T dashes, the coefficients A, B, C, D are different now. So it is further refined to have the better response here, this transformation function. So this is not 1 by 2 or 1 by 4 coefficients what we had in the previous example. This design procedure gives the better frequency transformation function to meet the specification. So this is one procedure. So this example one, which we will see as a code in the laboratory demos. So further details of the obtaining this T dash and the T in the previous example, the constant coefficients also, and the implementation of that we will see in the laboratory demonstrations. So now these are the three procedures which we try to use it in the FIR filter design 2D case: window method, frequency sampling method, and the frequency transformation method. Frequency transformation method, the first method assumes the frequency transformation function. In the second method, we find the frequency transformation function, and the better frequency transformation function depends on the specification. So now few MATLAB codes of these methods what we had discussed in this week will be helpful to design these filters. So we'll see that how do we get the frequency response of this 2D FIR filter, also the case of how to get the impulse response, how do we get the 1D response, how do we plot these windows and what different types of windows, how do you use that in the filter design, and so on. So in this Huang method, if you recall that we have taken the analog window, and for the to make the circularly symmetric window, so we had rotated it in the so by substituting T equal to T1 square plus T2 square root. If you recall the method we discussed in the few lectures back, then now using that Huang's method we will design the 2D FIR filter. So design of 2D FIR filter H, which is this H of n1 comma n2, are the frequency response of it. Okay, for the desired H of HD, that is the desired frequency response, using 1D Hanning window. So this window can be of any type, like Hanning window, Hamming window, or the separable window, and so on. So in this case, we'll take the circularly symmetric one, because Huang's method uses the circularly symmetric one. So the first creates the frequency space in the use the mesh grid of 21 points, that is F1 and F2. It can be of any number of points here. So R equal to square root of F1 square plus F2 square. So this is what the circularly symmetric one comes into picture. So the HD response is ones of 21. So the filter which is having the response of 1 for certain band and it is 0 for other things. So here it is 1 and R less than 0.1 and R greater than 0.5, this HD is 0. So that means you have this 0.1 to 0.5. Ideally this is omega and HD of omega. So this is in 1D I am showing it, but we will be doing this in the 2D case. So this is what is aimed here in this between R, between that this would be 1, 21 points and then the rest of them would be 0. So if this is the case, then what is the color map? Actually the case of visualizing this in the mesh grid with the color scheme. So color map is shown, this is with 64 of Parula, and it is just a representation here, the mesh of F1 comma F2 or HD. So HD we are plotting it using the mesh grid, F1 F2 frequency space generated here. So the case of next, what is the window function which we are going to use to get the Huang's method of the window, analog window, which is W, that is window equal to 0.5 cos 2 pi into 0 to 20 points, that is 21 points by 20. This is an Hanning window, and just plot this window in the space, linear space, making it from -1 to +1 and having the 21 points. That's a Hanning window. So this is the HD response, and we get here the window. The second one is just plotting the window, Hanning window, and then use this window and HD, the desired response and the window function. If you give that, this would F window 1 is actually a function, built-in function of the MATLAB to design this 2D FIR filters using the window method. So H would give the response of the coefficients of this, considering HD and the window, that is the desired response and the window function. And if plot this H, you can get the impulse response, or plot the frequency response of it, H frequency Z2, that's a command which you used for the getting the frequency response, which would it is real here. If you have the complex values also, it would result into the case of magnitude and phase. We can take the magnitude and phase separately also. So this is a frequency response which is which we get. So we can plot this desired frequency response, which is a circularly symmetric one. You can see that HD of this is a desired response. So we have given this desired response as this with the mesh grid plot HD, which is normalized. This F1 and F2 are normalized here. We can call it as omega 1, omega 2, or HD is omega 1, omega 2, or F1, F2, which we have used. So this is a normalized frequency here. And the case of for HD and the window function, what we had used is Wn for n, and this is continuous plot, and but there are samples of only 21. Number of samples have been taken for this Hanning window. So this Hanning window, and use this window, and the response what we got, 2D FIR filter responses F1 and F2 and H of F1 comma F2, or it can be of omega 1, omega 2, H of omega 1, omega 2. That's the response of frequency response of the designed filter with F wind 1 built-in function. This is the frequency response with the Hanning window. So you can see the response which is for the in between less than 0.1 and between 0.1 to 0.5, we have this band of frequencies, and then it is going to be the stop band here. These are the stop band, circularly symmetric, so the ripples are very less over here. You can see the ripple of Hanning window, which gives very low ripple, and this one is obtained from using the Hanning window, the window method, the first method what we had learned. So giving the 1D window, and use that 1D window for designing this 2D FIR filter. So the same thing, which if we change the window function, that with in the previous code, window equal to Hanning window, so 0.54, which is known equation, 0.46 cos 2 pi, this function of 0 to 20, 21 points by 20, and the frequency response of the filter design 2D FIR filter with the F wind 1, F wind WIN1, so would give us the response, 2D FIR filter response with the Hanning window. So you can see the ripple Hanning window here. First one was the Hanning window, and then this is the one which you can see the ripples, the difference in ripple for the same specification. We get this Hanning window. So Hanning was smoother compared to the Hanning window here. Now getting this filter design using the separable window. So design the 2D FIR filter with the for the given HD response and using two 1D windows, that is separable windows. So here we have used 1D window, and that one is used by fwin1 function, that is 1D window, and here we can use these two 1D windows. So get the 2D window, and then h of omega 1 comma omega 2 can be obtained from this HD and W frequency response. The W is corresponding to the window of 1. So let's see the plot of this. Have a frequency space, create a frequency space, and this is circularly symmetric. So the frequency response is circularly symmetric, which we can see, and but we are using the two different windows in the sense of two 1D windows. HD equal to 1s of 21, and the similar case 0.1 to 0.5 it is 1, and the remaining regions it is 0. So make the color map and figure which get the mesh grid that is same as the previous one. So only the window part which is different here. Window 1 is boxcar window, that is a rectangular window of 21 points, and window 2 is also boxcar of 21. This gives the 1D two 1D windows, and we can plot this win1 separately or win2 separately. Will have two windows and use this in the fwin function. So fwin1 function can have HD comma win. If you say one window, it will use it. It will use that for the making it as a 2D window and use it, or if you specify window 1 and 2 sort of separable windows, then it can give the separable response as well. So that's the circularly symmetric one, the first one which we had in the previous example. H equal to f window 1, HD win 1 comma win 2. So and get the frequency response of this. Frequency is 2H. So the response H, what we get here is, you can see the ripples over here, and you can see the separable window. The theoretically we had looked into where it is omega 1 and omega 2, right? This omega 1 and omega 2 are F1 and F2. In this region, the ripples would be more for the rectangular window. So this could be visualized clearly here. The ripples are at the center of W1 or W2 are the case of F1 and F2 in the frequency response. So this is the response for the separable window what we had obtained for the response of this. And if we have the same case with we can just replace it, the case of frequency space created for the circularly symmetric, and this can be of HD can be of circularly symmetric. You can use the separable window or the circularly symmetric window. We had seen the first two cases of circularly symmetric one, in which that hwin1 function has been used for using the window method, and the same win1 similarly for the separable window, two separate windows like Hanning window, win1 and win2, and use the same function which we had and the fwin1 at the desired response, and win1 and win2 the separable window Hanning window can be used. So the separable window, we mean that here get the frequency response of it, and the frequency responses, you can see that this window is also having the case of separable, because we used the separable window concept. So we have this ripples at the center of it. If it is circularly symmetric, it would be the more ripples with the circular fashion. So the case of frequency, this ripples will be at the center for the separable window. So separable window, it need not be of only the rectangular window, it can be of Hanning window as well. So if you use this for the window design method, this is one example also to create the separable window of any window type, rectangular or Hanning or Hamming, and then use that in the fwin1 function. So the next method which we have, this we keep it common, that is the frequency space what we had for the circularly symmetric HD space, it is same as that what we had done in the all the examples F1 and F2 and HD, and get this window method, in which the second method, so direct, we use the 1D windows in the previous cases, two 1D windows as well. So now we can use another function in which we can have the fwin2. fwin2 is directly designing the 2D FIR filter by having this HD comma win1. So in this win is going to be taken as a 2D window. So the 2D, this is going to be 2, it will take this as a 2D window. So in which window has to be specified, which can be specified with window has F special Gaussian, and give this is a Gaussian window in which you can have the number of points 21, 2. Okay. So it's specify that number of samples and then 2 as well, and find this window maximizing, normalizing this win by maximum of win all the values. So this would be win. Now just normalizing it to have the maximum value 1, and then use this in the f win 2 function hd comma win. So this gives the impulse response of it, and then take the frequency response. Frequency is it of h. So the difference here is that this is the f win 2 function, and that which uses the hd of omega and omega 2 and get the window function and its w of omega 1 comma omega 2, that is from the function what we specify here, 2D windows, not like 1D window what we had used in the previous examples. Not even the 2 1D windows are supported, or 1D window is supported in that case. Here it's a 2D window. The window is a 2D, and it directly takes this HD and window 2D to compute the FIR filter coefficients, 2D FIR filter coefficients, and the frequency response can be obtained. So this 2D window we would like to show it here. This N1 and N2, h of N1 comma N2 is a window function. This is a Gaussian window, and the frequency response obtained from that 2D window is this. This is with the Gaussian, so it's very smooth one. You can't see that the ripple in this stop band. So it's a very smooth, it's a filter of using this Gaussian as a filter. That is window function here. So this is the response what we had obtained from the design. So now taking the low pass filter design. So low pass filter, band pass filter, or the one which we had is the band pass filter. From 0.1 to 0.5 it is 1, and rest of the band of frequencies are not passed through it. So in this 2D separable low pass filter, how do we design this low pass filter with a separable frequency response? So we have the case of taking some points of f1 for the filter size. It can be of 21, 31, or the size it is meant here it is 41, and giving the cutoff frequencies normalized by pi here 0.5 and 1 by 3. So these are 1 and 2. It can be 2, 1 in any way. So taking the separable frequency response. So here HD is nothing but the case of separable response. So frequency space, when we create it, you can see the difference HD, which is double of absolute of W1, which is less than omega C1, and absolute of W2, which is less than omega C2. So these regions have to be taken care. That is W1 and WC1 and WC2, the less than or equal to regions should be 0. Other cases should be 1. So other values should be 1. So that's what HD specifies. So from this HD, use the frequency sampling filter to f samp 2. So this method gives this frequency sampling built-in function to use it in the design. So this is an h of h is the case of impulse response what we get from the HD, and this is a separable response. It's not the circularly symmetric response what we had done in the previous examples. So this is a case of separable response, and the sampling method to design, the method which we are using to design it is a frequency sampling method. So frequency sampling method, we had seen the comb filter and the resonator structure. So this uses the comb filter and the resonator structure, the combination of this in 2D, and making this impulse response of the desired frequency response HD. So f sample 2 is the built-in function used for designing this frequency sampling method. So these are all the just plotting this. How do we plot the response, separable response, and the frequency sample filter as well. So it's just some parameters which can be used to plot the this is the response, frequency response of a separable case, so separable frequency response. So which omega C2 and omega C1 we have defined, and after this this is the width and the breadth of this filter, below which these values are omega C1 less than that and omega C2 less than that, all would be 0. This is only 1. So this has the frequency separable response for this response, and we choose the frequency sampling filter in which we have obtained the sinc functions. If you recall, those things are whatever the k values we need, those needs to be having the frequency response, contributing to the frequency response in that sense. So this is the impulse response what we get. So this is separable, so you can see the ripples of this at the center of the response. Okay. So H, and if we try to get the frequency response of it, if this is same as the frequency Z2, so for the H what we had already, and get the frequency response, so H of f, and get the magnitude and phase if you want separately. This is the absolute of this, getting the normalized value, and plot for the plotting of omega 1 versus omega 2 instead of f1 f2 in the unlike the previous cases we have plotted with f1 f2. Now this plot is up with respect to w1 and w2, or omega 1 and omega 2 radian frequency. So these method of frequency sampling method results in the separable window response. You can see the frequency response which is separable, which has the center ripple, and the frequency sampling method which is giving very crude way of, because of the selection of this k that we can get, we can see this ripples, high ripples in the passband as well. Okay, and then so this is the response of the H of omega 1 omega 2 for the separable frequency response using the frequency sampling method. And we can also have this circularly symmetric filter response, in which we had done this previously. So, but the number of filter size which is taken as 61, and have the cutoff frequency, and create this grid of this mesh grid which we had done in the 1 to 3 that examples, and HD is taken as for certain values of this. This is a low pass filter frequency response. Band pass we did, and then this is low pass. So for a particular less than omega c, these values are, otherwise it is 0. So using the frequency sampling method, this is HD. I use this f sam 2 represents this 2D. Similarly, f win also 2 we had, that is directly taking the 2D window. F win 1 also designs the 2D FIR filter, but using the 1D one, that is a Huang's method, using 1D window and make it as a 2D in that case. So H is equal to this impulse response, and once we have this impulse response, get the frequency response of it. So these are the properties used for the plot, and we had the response plotted in this case. Like this is the circularly symmetric response required, HD of omega 1 omega 2, and the impulse response from the frequency sampling filter response is this. Just circularly symmetric, so you can see the circles over the ripples of like kind of thing in the response of H as well, and then the actual frequency response can be obtained from using this H, and the built-in function is frequency C. So change this f1 f2 to omega 1 omega 2 for the case of plotting. So the response what we have is this. So this is a case of circularly symmetric. Again, because of the number of resonators, and you can see that these plots have the very crude way of having the passband and the stop band cases. So, but we can have this circularly symmetric response in this low pass filter. You can have this also. These are the different way of designing the 2D FIR filters. One is the frequency sampling method, and the first one we had seen different types of designing the 2D FIR filter for the using the window method. Also the frequency transformation method we will do through the demonstrations. We have just completing the FIR filter design, 2D FIR filter design, in which the first method of window method, and the frequency sampling method, and frequency transformation method. Frequency transformation method, we had found the frequency transformation function, that for deciding the region of support of this frequency transformation function, and using that frequency transformation function and the filter design in 1D using the specification of 2D, get the either through the window method or the Fark-Maxwell method. That Fark-Maxwell method can be obtained from this MATLAB built-in function also. FIR PM is the command which can be used to design it. Once we have this H of n and T of n1, n2, you can get the 2D filter coefficients H of n1, n2. So that procedure, the plotting of the frequency response and other things we'll do in this demos. But we had gone through the codes of this implementation using the frequency sampling method and the case of window method in different cases. We'll continue with the IIR filter and its design in the next lecture. Thank you.